Hi everybody, welcome to another video in differential equations, section 0.4. This section we study inverse Laplace transform. So we have the table of Laplace transform over there. So we have the transform of 1 is 1 over s. Transform of e to the at is 1 over s minus a. Of course, previously we write out the condition for this s being positive and s greater than 8, those things. Next, transform of a power term, and so those easy to recognize, easy to do, easy to remember when we do enough problem. How about sine, cosine? Remember, just like derivative and integral, derivative of sine is cosine, integral of cosine is sine, so switching between sine and cosine. Alright, so how do we memorize this? So how do I memorize this? So what I memorize is that sine is an odd function, cosine is an even function. These two functions, b is constant on the top, so this is going to be an even function, and s on the top, so that is an odd function. So a transform from an even function, it would be an odd function. Transform of an odd function is an even function. Just like derivative of an in general it does not work. I'm just talking about sine, cosine, and in this context here, right? So just like derivative and integral of sine, cosine, derivative of sine is cosine. It goes from an odd function to an even function. In that context, in general, of course, it's not going to work like that, but just the way to memorize this, sine is an odd function, the Laplace transform will be an even function, which will be this one, and cosine is an even function, Laplace transform is an odd function, which is that. Right? Like I said, it only works in that context. Now with that, let's go to define the inverse Laplace transform. So given a function capital F in terms of s, if there's a function such that the Laplace transform of f is equal to capital F, then we say f of t is the inverse transform of f of s. So the inverse is given like this. Or if we want to, if we put on the Laplace transform, again, this is the script L transform of f. The variable is t, or just put parentheses, is the function in terms of s. Now this is f of t, where this is the variable of s. Of course, the inverse will give us the function in terms of t. Of course, if the variable is it's clear to the context, we don't even need to write t and s. But the function, original function, is in terms of t, the Laplace transform in terms of s. If we want to go inverse transform, we go from s to t. Right. Now, so what is the Laplace transform of this? Of course, if we look on the table over there, we just go from the right column to the left to find the inverse. Right. So what is the inverse of this? Now we can rewrite this as 2 is the same as 2 factorial, and 3 the cube, we can say 2 plus 1. So the reason we write like that, so the form of Laplace transform, we're talking about this 2. So inverse Laplace transform of 2 to the s cube is going to be t to the n. So script L inverse of 2 over s cube is the same thing as Laplace transform, inverse Laplace transform of 2 factorial over s, 2 plus 1, and that is t to the n, which is 2, so that is just t squared. Right? So on that table, we look from right column, go to the left. Right. Next, we have this one, Laplace transform of 3 over s squared plus 9. S squared plus 9 we can write as 3 over s squared plus 3 squared. Notice that in the Laplace transform of sine cosine, we need to have s squared plus b squared at the bottom, and then if there's a number on top, those should be the same. I'm talking about b and b squared here. Right. So, by the way, that is an even function, so the inverse Laplace transform is going to be an odd function, so this will be sine. Right, so inverse Laplace transform of 3 over s squared plus 9 is the same as inverse Laplace transform of 3 over s squared plus 3 squared. And that will be that. So both of these numbers are the same, which is the b in this case, so b is 3, and we have sine of bt, sine of 3t. Right? So that's easy. Now we have s minus 3 cubed. So what's that? Right, first of all, remember we have the Laplace transform. Let me write out this from previous section. So if we have the Laplace transform of a function, yeah, I mean that this is exactly what we have here. We have the Laplace transform of a times at to the function, right? So the transform of that, first a to the at, just ignore that. What we do is we just find the transform, meaning, just do the transform of f of t, ignore that part. But once we done that, we replace s to s minus a, and that's what the e to the alpha, e to the at does. Just ignore that, transform the function, and at the end replace s by s minus 8. Now the inverse Laplace transform, we have to do this in the opposite way. By opposite, I'm not meaning positive or negative, I mean in the reverse direction. So first of all, of course, this is 2 over s minus 3 cubed, right? Actually, we just jump right into the problem. Now let's find the inverse Laplace transform of 2 over s minus 3 cubed. Right. First, what we see here is s instead of s minus 3 instead of s. So if we replace s by s minus 3 or s minus 3 to s, so we say if we replace s minus 3 to s, what we do here is from that part we can just write down e to the at, e to the 3t. Once we do that, sorry, forgot the inverse Laplace. So when we see the s minus 3 like this, so write out that out, s minus 3 replace to s. When we do that, we replace, we multiply the a to the at into the function, and then we just do the inverse Laplace transform of the same function, but instead of s minus 3, now we're just going to use s of 3, I mean s cubed, which we already did, which is t squared. So we have e to the 3t t squared. So every time we have the s minus something, if we replace that back to s, that is the price we pay is e to the at. right? Because that we go from that table over there, we go from right to left. Right. Now we have this. Now we have s squared plus s squared minus 2s plus 5 at the bottom. So this, we have to take care of this first. And let's take a look at the graph. X squared minus 2x plus 5. We see the graph that is above the x-axis, meaning there's no x-intercept, meaning there's no real solution. So we cannot factor. If we cannot factor, what we can do is completing square. So we do is completing square. So we start with that. To complete a square, we will need to add something and subtract the same thing to make a square. And whatever that something is, it's going to be half of the middle numbers. So take half of that, and then we square it. So half of 2 is 1. 1 square is 1. So we add 1 and have to subtract 1. So let me rewrite this. So we have s squared minus 2x plus 1 minus 1 plus 5. Now, the first 3 term will be a complete square, or we just have to carry this number down, subtract. I mean, this sign will go down, and that will be a square. And then we have minus 1 plus 5 is plus 4. Right. So completing square of s squared minus 2s plus 5 is going to be that. So now we find the inverse Laplace transform of s minus 1 s squared minus 2s plus 5. Right, first, of course, completing square replaced into s squared minus 2s plus 5. S minus 1 square plus 4. 4 is going to be 2 square. Just plus 4 for now. Now, notice that both of them have s minus 1. So if we replace s minus 1 by s, the price for that is going to, we multiply by e to the, if we replace s minus 1 by s, we multiply e to the 1t. In that case, we no longer have s minus 1, we just have s. 4 is 2 square. Right. So if we replace s minus 1 back to s, the price to pay is e to the at. So this case just e to the t. Now, this is the Laplace transform. This is an odd function, Laplace transform. That will be an even, which will be cosine. So this will be cosine of 2t. Yeah. So we're talking about that one. All right. The b in this case is 2. Right. Of course, we can also have directly look at this formula and Laplace transform. Of course, from right to left. That's exactly what we have here. Right. Next, we have the properties called the linearity properties. This property will. This properties is there for the limits, derivative, integral, Laplace transform, and inverse transform. Meaning that inverse Laplace transform of a sum is the sum of the inverse Laplace transforms. We can take the constant outside. So this is exactly like derivative, like integral, like limits, like summation, Laplace transform. Now the inverse Laplace transform. Right. Now, let's find inverse Laplace transform of this one. So a little more complicated, but first let's do the s squared plus 2s plus 10. Again, we try to factor it, but if we cannot factor, do the completion square. So let's look at the graph. X squared plus 2x plus 20 once again, there's no x-intercept, no real solution, cannot factor. So what we do here, because first thing we do is completion square. S squared plus 2s plus 10 add something, subtract something, and that something is half the middle term square. Half of the middle term, half of the middle numbers, half of 2 is 1, 1 square is 1. So in this case, the first three terms will be a perfect square trinomial s plus 1 square minus 1 plus 10 plus 9. S minus 1 square plus 3 square. Right, so that is, we completed the square there. Right, now go back to our problem for the inverse Laplace transform of this. So we have 3s plus 2. The bottom will be this one, which is the same thing as. Let's just copy the problem. Now, the bottom is s plus 1 square plus 3 square. Right, the top is 3s plus 2. Now, similar to the previous problem, we try to manufacture the s minus 1 in terms of s, or the s minus a in terms of, replace that into a s, and then we can go from there. However, this is a little more complicated. We have 3s plus 2 on the top, so we have to do a little creative here. The bottom we know is still the same. We're not going to mess with that. On the top we do need to have s plus 1, so we're going to have 3. Right, now this is the creative part. The s. If we're going to add something, we're going to subtract something, so we need to have an s here, right? If I'm going to add something, that have to be the same as 1. So we want to manufacture the same thing at s plus 1 at the bottom. But we cannot just add 1 times 3, so we cannot just add 3 to it. If we want to balance it, 3 times 1, we plus 3, we have to minus 3 to keep things balanced. Right? So that will be 3s plus 3 minus 3 plus 3 minus 3 cancel out. So that's why we have to do that. And then we have the plus 2. Alright, now let's rewrite this. Inverse Laplace transform 3 s plus 1 minus 3 plus 2 is minus 1. The bottom, s plus 1 square plus 3 square. Now both of them have s plus 1. If we replace that, what we have to do is, by the way, s plus 1 we can write s minus -1. So we write like that. That will be replace s minus -1 by s, so that we have to have a to the negative t. Right. Replace s to the -1 t. In that case, we will just have the 3s minus 1 over s square plus 3 square. Right. So replace s plus 1 by s by multiply by e to negative t. So that is the transform that we need. Right. Now we have e to negative t. Now for this one, remember we have the sine, cosine. Talking about these two. One of them, the top is b, the other one, the top is s. So in this case, I have to split this in two because using the linearity here. So we split the 3s. Then split the 1. Right? 3s minus 1. Right, so that's good. Right, next, in the Laplace transform, if this is s, it's just s on the top, so we will take the 3 on the outside here. And then notice that in the Laplace transform, if the top is a constant, let's focus on this notion. Focus on that. Let's focus on that. If we have b squared at the bottom, the top have to be have b. So if we just multiply by 3 here, cannot just do that. If we multiply by 3, we have to divide by 3. So we have to do that to have the numbers here the same, and we just have s. So let me rewrite this. We have 3 inverse Laplace transform of, now we only have s on the top. And then we have minus 1/3 inverse Laplace transform of 3 s squared plus 3 squared. Now you see, if the s on the top, s which is by itself, if there's a numbers, that number must match with that number square, must match with what we have at the bottom. So that's why we multiply 3 and divide by 3 there, to have those numbers match. Now e to negative t, 3 transform of this is an odd function. The Laplace transform is going to be an even, so it's going to be cosine. Yeah, because the formula is over there. Cosine of 3t right, then minus 1/3, and this is an even function. Inverse Laplace transform is an odd, meaning the sine of bt b3, so sine 3t. Right, so that's what we have. Right, similarly on this one, s squared minus 4s plus 20 should do the completion square as well. S squared minus 4s plus 20 need to add something and subtract something, and that whatever that something is half of this number. Half of 4 is 2, 2 squared is 4, so we're going to add that. Once again, half the middle number square, half of 4 is 2, and then square that number, add and subtract. Now with that, the first 3 will be the perfect square trinomial. In particular will be s negative 2 minus 2 square plus 4 minus 4 plus 20 is plus 16, which gives us s minus 2 square plus 4 square. Right, so that is the completeness square. Right, now we will do that. Inverse Laplace transform of 5s minus 1 over s squared minus 4s plus 20. First thing, of course, replace the denominator with that. Next, we need to manufacture the s minus 2, so we can replace it with the exponent like that. So inverse Laplace transform right, we have 5s, so we need the minus 2, so that will be the same, and we cannot just subtract 10 like that. If we subtract 5 times negative 2, so that is minus 10, we have to plus 10 to keep things balanced. Then minus 1. Right. So that gives us inverse Laplace transform of 5 s minus 2. 10 minus 1 is 9. S minus 2 square plus 4 square. Now what we will replace is s minus 2. Replace into s. When we replace s minus 2 into s, what we need to multiply is e to the 2t. Yeah, so always s minus a number, s minus a, and then e to the at. Alright, so with that, instead of s minus 2 replaced by s, and the price to pay is e to the 2t. And then in that case, we no longer have s minus 2, we just have s. Five s plus 9 and then s squared plus 4 squared. Right, so that's good there. And then we'll split using the linearity property. Even better with the coefficient. The 5s, so I have 5 inverse Laplace transform of s. So we split the 5s and then take the 5 outside, and then take the 9 outside as well. So we just have 1 over s squared plus 4 squared. Yeah. So linearity 5 times s over that, and then plus 9 times 1 over that. Now, what next is, of course, we know this is the inverse transform. That is R, so the inverse Laplace transform of this is going to be cosine. Right? Talking about that one. And this will be inverse Laplace transform of that going to be sine. However, we will need the 4 here. Those numbers must match. So multiply by 4 and have to divide by 4. Because this number must match with the number at the bottom. We write this, we have e to the 2t 5 times inverse Laplace transform of s squared plus 4 squared plus 9 over 4 inverse Laplace transform of 4 s squared plus 4 squared. So e to the 2t and then 5. This is the in the form over there. That should be cosine of bt, b being 4, so cosine 4t plus 9 over 4, and then this is sine of bt, where b is 4, so sine of 4t. Right. So that is the inverse Laplace transform. Now, what we have more complicated is what if the bottom we cannot do the complete square, but we can factor, and that is completely different things. In that case, we're required to do partial fractions. To review partial fraction, so doesn't matter what polynomial we have at the denominator. If we can factor, it can be factored using the linear factors or quadratic factor. It cannot be more than that. At the high level, we can see that it can be factored. Any polynomial can factor into linear and quadratic. It will not be a qubit. A qubit factor can always factor to something smaller. Right. So if we have a linear factor, then we just have the linear factor at the bottom. And then the top, if this is a ratio, if the top degree have to be less than the bottom, so we just have a constant on the top. If we have a repeated factor of x minus a, then we just have repeating that factor up to the end of the multiplicity, and on the top we just place the constant on top. For quadratic, if we have a quadratic, then we have the top is a linear function. If we have the repeating, then we'll have those repeating up to the multiplicity of n, and then on the top we place the constant, I mean the linear function. Remember, degree on top is always less than degree at the bottom. Right, so now let's look at this example. Write out the form of the partial fraction. Do not solve for the coefficient. So that this we have a linear factor and a quadratic factor. So in that case, this is easy. We just have a linear factor and a quadratic factor. Simple enough. Degree on top have to be less than the bottom. So here we can say a just a constant. If it is quadratic, we can have a linear function. Just like that. Now, this will be a little bit different. What we have here is a linear factor to the cube and then quadratic to the second. So this is the cube for the linear factor, meaning we're going to have 3 of them. Increasing power from 1 2 and 3 to accommodate the 2x plus 2 cube. If that is repeating, that's what we have. On the top, just a constant, different constant. Right, now we go to the quadratic. For the quadratic, there are 2 of them, so we'll need 2 of them. By the way, this cannot be factored any further. So we have 1 to the first power. And then square. If we have this to the third power, we will need one more term raised to the cube, the third power. So that's what we have. This to the square. So first, second, this cube, 1, 2, 3. Right. Now, on the top, if this is quadratic, the top has to be 1 degree less than that, have to be less than that, so it should be a linear function. We will not want to use d here because d is reserved for the derivative, the operator, right? So let's skip d to ex plus f. And then here also the same order of polynomial, so gx plus h. Right. So that is the form of the partial fraction. When we multiply both sides by the common denominator, in that case we can so for the coefficient, once we have the coefficient, we can find the Laplace transform. So this is what we're going to do here. I'll find the following inverse Laplace transform of that. Okay. So first, we have to do the partial fraction. The first step is the partial fraction. So we write s squared plus 9s plus 2 over the bottom of s minus 1 square s plus 3 right. Now, if we decompose that, s minus 1 to the second power, so we should have two of them, s minus 1, s minus 1 square. And then we have one factor of s plus 3. So we just have one factor of one fraction of s plus 3. On the top, degree will be 1 less than the bottom. So this is linear function to just have a, b, c here. Now, the rest is easy. Multiply by the common denominator, which is this, on both sides, and simplify. So the least common denominator will be s minus 1 square s plus 3. So I multiply both sides by that. If we multiply that, this cancel out, we have s squared plus 9s plus 2. Now, here we have multiplied these two terms. One factor of s minus 1 cancel out. So we left with s minus 1 and s plus 3. Right, for b. If we multiply out, s minus 1 cancel out will be s plus 3 that's all, right? And then c, we have s minus 1, s plus 3 cancel, we have s minus 1 square. Right, now just multiply it out, match it, the coefficient, and solve it. So this is like what we did back then when we do the undetermined coefficient, and that's exactly what we do here. It's called the undetermined coefficient. Right, I'll multiply this out. S minus 1, s plus 3, s squared plus 3s minus 2s plus 3 minus 1 plus 2 minus 3. Simple enough, right? Right. Multiply this out. bs 3b s minus 1 square s square minus 2s plus 1. Of course, we did the completion square, so this is just reverse of that. Right. S minus 1 times S minus 1 is this. Right. S minus 1 times S minus 1 is going to be this. Now, multiply it all out. AS squared 2AS minus 3A plus BS plus 3B CS squared minus 2CS plus C. Right. Of course, the left hand side is still S squared plus 9S plus 2. Right. Now we just need to match the coefficient. First of all, let's group on the S squared. So we have A plus C will be S squared. Right. Now, next, S 2AS BS minus 2CS, just have a plus 2A plus B minus 2C S. Left with the constant negative 3A plus 3B plus C. Negative 3A plus 3B plus C. Right, so that's what we have. Now we just match with the coefficient on the other side. For S squared, we have an S squared, the coefficient here is 1. So we have A plus C is equal to 1. Next, 2A plus B minus 2C times S must match with this 9S. So we have 2A plus B minus 2C is equal to 9. And finally, negative 3A plus 3B plus C have to equal to 2. So we have that system of equations. Right. Remember, when we did this in the previous section, we used the calculator, and I will do that same thing. Coefficient for A, B, and C should be 1A, no B, 1C will equal to 1 on the other side. Next, 2A, 1B, negative 2C equal to 9. Negative 3A, 3B, 1C equal to 2. And after that, we do the reduced row echelon form. Right, so I use the calculator here. First, okay, I do the, if you calculate TI-84 plus, then you can have this option. I will go second matrix, sorry. Go to math, reduce row echelon form, like that. Now I will enter the matrix alpha zoom. This is 3 rows and 4 columns. So input the matrix there. 1, 1, 1, 2, 1, negative 2, 9, negative 3, 3, 1, 2. Hit enter, and that's what we have. 1, 0, 0, 0, 1, 0. If we have the diagonal matrix on the left hand side, then on the right hand side we have the solution A, B, and C. Right. So if your calculator cannot do this, we have to store into the matrix. So hit second matrix and go to edit and store the values. So this is a 3 by 4, 3 by 4, 1. In this case, we have to hit enter. 1, 0, enter, 1, enter, 1, enter, 2, 1, -2, and 9, -3, 3, 1, 2. Right. Once we enter all the numbers in the matrix, second mode to quick. Now if we go back to matrix, second matrix, we see the 3 by 4 matrix there. If we hit enter, that where we recall it. Right. Now the same thing. Second matrix, go to math, go down to option B, reduce row echelon form. And then we just hit second matrix. We apply that to the matrix A. So in the names, highlight that and hit enter. So if we want to input the matrix, we go to edit and input the matrix. If we want to recall it, go to names, highlight it, hit enter. Now we do reduce row echelon form for matrix A. And of course the same thing we have here. So either we put the matrix directly in the home screen or we store it into the matrix. It still do the same thing, and we have A, B, and C here. So bottom line is we have the partial fraction. So the partial fraction, we will have s squared plus 9s plus 2 over s minus 1 squared s plus 3 equal to A is 2 over s minus 1 plus B s minus 1 squared and C -1 s plus 3. Now put all of that together, we do the inverse transform. So inverse Laplace transform of this will be inverse Laplace transform of the little fractions 2 B3, right? Now, just split them apart because of the linearity of inverse Laplace transform. And we can even take the 2 outside. Take the 3 outside. Now, we have s minus 1. If we want to, we can use this formula. And so that will be Laplace transform. That will be e to the at. That's simple enough, right? Or for this one, if we replace s minus 1 into s, we will multiply by e to the t. So we have 2 e to the t, and we just do the Laplace transform of inverse Laplace transform of 1 over s. So replace s minus 1 by s. The price to pay is e to the t. Same thing here. Replace that s minus 1 into s by e to the t. And so we have just 1 over s squared. And now s minus negative 3 replace into s by multiplied by e to the negative 3t. Of course, this you can go directly e to negative 3t. That's easy. Yeah. Inverse Laplace transform of 1 over s, the one right above it, it's just 1. So this is equal to 1. And this, if we write that, so we have 2 e to the t plus 3 e to the t. Now for this one, if we rewrite as 1 factorial over s of 1 plus 1, the inverse Laplace transform of that is a t. This is just 1, so we have e to negative 3t. Bottom line is we have 2 e to the t plus 3 e to the t. Inverse Laplace transform of this is the next one. When n is equal to 1, when n is equal to 1, so we just have t, pretty much, right? 1 factorial over 1 plus 1, so times t minus e to the negative 3t. Yeah, so this inverse transform is a t to the first power. Right, so we do the partial fraction, and after that, so for the coefficients, once we split that into a little fraction, we can apply the inverse Laplace transform to it. So that's simple enough. Next we do this one. So first I do the partial fraction. Oh, by the way, I should mention this real quick. At this step, if we focus here, there's another way. If the problem is simple enough, we can do this to solve for coefficient easily. Notice that this expression, if we let s equal to 1, so if we let s equal to 1 for that equation, s minus 1, so that one go to 0 and that one go to 0, right? When s equal to 1, those two go to 0. S equal to 1, the left hand side, I'm just going to substitute in 1 square plus 9 times 1 plus 2 equal to a s minus 1 s plus 3. This, because of s minus 1, go to 0, plus b s is 1 plus 3 plus c 1 minus 1 square. Again, that goes to 0. So simplify, we have 1 plus 9 plus 2, so we have 12 equal to 1 plus 3 is 4, 4b. So in this case, we can get b equal to 3 easily. And in this, we have b equal to 3. Right? So when the problem is simple, we can just choose some simple numbers. Put in that, eliminate a lot. Next, if we let b equal to negative, if we let s equal to negative 3, those two terms will disappear, and we can solve for c. S equal to negative 3, right? Negative 3 here. And of course that will go to 0. Negative 3, negative 3. Okay. Negative 3 plus 3, so that goes to 0. Plus b, negative 3 plus 3 also goes to 0. And then plus c, minus 3 minus 1 square. Right, minus 3 square is 9, minus 27, minus 18, plus 2, minus 16. This side, negative 3 square, negative 3 minus 1, negative 4 squares, that's 16. So c must be negative 1. Yes, so c is negative 1. Yeah, so if the equation is simple, we can just choose some values and then substitute in. So we do that, we have b is 3 and c is negative 1. Then we say, how do we find a? Well, to find a, when we know b and c should be easy. We can substitute b and c in here, and then we choose a, choose something for s. That does not make this disappear. I could choose a to be, like say 2, for example. We can put 2 here. We know b, we know c. Put 2 here. We can actually solve for a. Right. But since I have the calculator, more systematic. If the problem is complicated, multiply it out, combine like terms, and use a calculator to solve for that. Works just as good. Right, now, wait, sorry. This is the next problem. So first we do the partial fraction. 1 over s and s squared plus 4. There's a linear factor of s and the quadratic factor of s squared plus 4. So we will need a constant term there for quadratic. We need the linear function on top. Multiply top and bottom by the linear least common denominator. Right, so we multiply that out. This cancel out, we have 1. And then a, s and s cancel out, we have s squared plus 4. And then s squared plus 4 and s squared plus 4 cancel out, we have bs plus c times s. Right. Now, for this, if you choose s to be 0, then that disappear. We have 4a equal to 1, so a is equal to 1/4. Right? If s equal to 0, and then you can choose something different. But since this is simple enough, I just multiply it out. As squared plus 4a equal to bs squared plus cs. Now just combine like terms. As squared, bs squared, factor out the s squared, and then we have a cs, and then just for a. On the right side, we just have 1. Right, now matching the coefficient. Now we match the coefficient. There's no s squared on the other side, so we just say 0 s squared. So we have a plus b must be equal to 0 because no s squared on the other side. Next, for cs, there's no s here. So we will match with 0. And then finally, for a, match to 1. Right, don't even need the calculator here because for a equal to 1, so a is equal to 1/4. C is equal to 0, we already have that. Now substitute this in here, where a equal to 1/4. We have 1/4 plus b is equal to 0, so b is equal to negative 1/4. Simple enough, right? A, B, and C. And C is 0. Right, so we have the partial fraction. Right, now we'll get back to the inverse Laplace transform. Inverse Laplace transform of this, it's just inverse Laplace transform of the little fractions. Right, the linearity of inverse Laplace transform, I will take 1/4 out. And then split and take the negative 1/4 out. Right? So in that case, 1 over s, Laplace transform is just 1, so we have 1/4. And now, this one, remember if we have s squared plus 4, you can write 4 as the 2 square. So we need a 2 on the top. If we need a 2 on the top, so that will match with the number at the bottom. We cannot just multiply 2 on the top like that. We have to divide back by 2. In that case, negative 1/4 and 1/2 put together is 1/8. In that case, we have the inverse Laplace transform of 2 over s squared plus 2 squared. So we have 1/4 minus 1/8, and Laplace transform of that will be, the constant on top. So constant on top, that number match with the bottom numbers square. So this will be sine. Wait, did we? Okay, sorry, I made a mistake there. B is negative 1/4 and B we have an S here, so sorry. That changes everything, sorry. B, so that should be just S. Right, so this is not 1, it is S. Sorry about that. So this should be negative 1/4 S. And if it is S, we do not need an 1/2 here. We do not need that. And that is the transform of cosine. If this is S, we do not need to multiply or divide anything. Transform of this is 1/4 minus 1/4, and transform of this is just cosine of 2t. Right, sorry about that. Notice B is the coefficient of S, so we have negative 1/4 S. C is equal to 0, so we don't have anything there. Right, so that's what we have for that problem. Right, next, find the Laplace transform of this one. So first, of course, we do the partial fraction. To s squared plus 10s, s plus 1, s squared minus 2s plus 5. S squared minus 2s plus 5, it cannot be factor anymore. It is a perfect square trinomial. I think we did that earlier. So if it is reduced, then we just leave that alone. We will not do any further factor. Let's say if we have something like I say we have that. Then first we have to look at this to see if we can factor that any further, and the answer is yes. So s squared minus 6x plus 5 gives us s minus 1 and s minus 5. So we have to factor first if we can factor it first. This problem we cannot factor anymore because that is irreducible. We can check by look at the graph. If there's no x-intercept, you have to see it is above the x-axis, so there's no x-intercept, no real solution, cannot be factored. Right. So we have one factor of s plus 1 and one factor of s squared minus 2s plus 5. On the top we have degree 1 less, so we just have a constant here and the linear function there. Multiply top and bottom by the least common denominator. So we have 2s squared plus 10s equal to s plus 1 cancel out. We have a times s squared minus 2s plus 5. And then we have s plus 1 because the quadratic factor cancel out. We have s plus 1 bs plus c. Right, multiply it out, combine like terms. As squared minus 2as plus 5a bs squared plus cs plus bs plus c. Now, we have square, factor out the s squared, and then for the s we have minus 2as, cs, and bs, minus 2a plus c plus b factor out on S, and then what's left is just 5A and C. And we have 2S squared plus 10S on the left hand side. Now we match the square with the square. Both of them have S squared, so the coefficient must be the same. A plus B must be equal to 2. And then the 10S matching with that, negative 2A plus B plus C equal to 10. And then there's no constant, so we just match with 0. Right, here I will use the calculator. I set up the matrix 1A, 1B, no C, equal to 2. Negative 2A, 1B, 1C, equal to 10. 5A, no B, 1C, equal to 0. And do the reduced row echelon form. Right. Second matrix, go to math. I'm going to do everything in the home screen though. Reduced row echelon form. And then alpha, zoom. I prefer to enter the matrix here directly. So alpha, zoom. And then 3 rows, 4 columns, so that's right. Now, in this home screen environment, do not hit the enter when you're done. Just hit 1, use the arrow. 1, 2. This is a negative sign. Do not use the subtract sign. And 5, 0, 1, 0. Right, when we're done, only when you're done. When we're done, hit enter. And that's what we have. The left hand side we do have the diagonal matrix. Then we have negative 1, 3, and 5. A equal to negative 1, B 3, and C is 5. Right. So we have the partial fraction decomposed. Partial fraction decomposition will be S. A is negative 1. B is 3 and C is 5. 3S plus 5. S squared minus 2S plus 5. Right. Once we decompose them, we can find the inverse Laplace transform. Inverse Laplace transform of this. We can split this in 2, just in 2. Don't split this yet. Right. Now this, because we take the minus 1 outside, then we just have 1 over S plus 1. that is the e to the negative t. Now, s squared minus 2s plus 5. Did we do that earlier? Yes. S squared minus 2s plus 5 is s minus 1 squared plus 4. So we did do the completion square earlier. That's what we have. So I will write at the bottom. I will use s minus 1 square plus 5 plus 2 square, sorry. Now, in that case, I will need the s minus 1 on the top as well. So minus 1. Again, not just minus 1 like that. 3 times minus 1 is minus 3. Again, not just minus 3. So I have to plus 3. Keep things balanced. And then plus 5. Right. Let's solve for this. Right. Now, we have our inverse Laplace transform. This gives us 3 of s minus 1. 3 plus 5 is 8. And s minus 1 square plus 2 square. Now, let's do the transform. Translate. If we replace the s minus negative 1 into s, the price for that is e to the negative t. So in that case, we will have negative e to negative t, and the transform is just 1 over s. Instead of s plus 1, we replace into s. Oh, where's the... Right. Now, this, if we replace the s minus 1 into s, the price for that is e to the t. So instead of s minus 1 replacing to s, we will have e to the t inverse Laplace transform. Instead of s minus 1, now we just have s plus 8. 3s plus 8 s squared plus 2 squared. Inverse Laplace transform of 1 over s is 1. Or we can just say inverse Laplace transform of this is e to the at, where a is negative 1. So we're just going to use this second formula. Just 1. Just e to negative 1t. So yeah, just use directly from the right hand side here to the left side. Just e to negative t. Right, so that gives us negative e to negative t, and then e to the t. Now we split this in 2. Inverse Laplace transform of s squared plus 2 squared. Right, so we split the 3, and then we split, and then 8 inverse Laplace transform of 1 over s squared plus 2 squared. Right. Now, the s is fine. That is inverse. If it is s, that is the inverse Laplace transform of cosine. If this is constant, it will be inverse Laplace of sine. However, whatever that is, the number must match with the number at the bottom. So I multiply by 2, divide by 2. So in that case, I will have e to the negative e to negative t plus e to the t, and then we have 3. That is inverse Laplace transform for cosine of 2t, and a over 2 is 4, and 2 over s squared plus 2 squared, so that is inverse Laplace transform for 2t. That's what we have. Now, of course, when we split, just split that. But if there's s on the top, we don't need to multiply or divide by anything. But if it is just a constant on the top, make sure that constant must match with the constant at the bottom. Bottom we have 2 squared, so we need 2 on the top. Multiply 2 on the top, divide by 2 at the bottom to keep things balanced. So we have 2 on the top, 2 at the bottom, keep things balanced. Right. And then we just find the Laplace transform for that. So that's what we have. So in this section we have the inverse Laplace transform. Most of the transform though is of the fraction, so we have to do partial fraction to split that into a little fraction, and we can apply the inverse transform for the little fractions. So that's what we have for the problem. Right. And apparently the partial fraction is the longest step when we solve the initial value problem. We will get back to a differential equation in the next section, but for now, in this section, we only learn about inverse Laplace transform. As always, thank you for watching, and see you in another video in differential equations.